me just remind you briefly what we're talking about. So the problem in general is you keep finding, so you're given these. So you're given in general these input sequences. So one, these are the assumption is the simplified assumption here is that each of these DNA sequences contain a line inside, and we're looking for that motif. Read of this.
So the cross is best the cross.
This one?
Yeah. Oops.
So we talked about the typical output of the motif finder. So what's the schedule like? I mean, it's pardon? So should I shorten it? So these are the alignments of the sites. I identify alignment of sites with the motif. I summarize the alignment using this matrix, and I further, from this matrix, I can further compute the entropy information content or entropy score, which is given right here in this object right here. So it's the sum of W columns, and for each column I evaluate the difference between the empirical frequency table of that column and the background frequency table. And we talked about the fact that ideally in this context what I like to compute is the p-value would be the probability of finding such a motif or such an alignment or better, and by better I mean that has an entropy score as great as the one I see or higher. And the null model is that the DNA sequences are independently generated, each one according to the background model. And I said that we don't know how to compute this p-value, so the idea of searching Stonewall was, well, why don't we compute the so-called p-value, the expected, rather than the probability of the input set containing an alignment of score greater or equal to S. Let's compute the expected number of alignment greater or equal to S. And we talked about the fact that in BLAST it works very well, and the reasoning is that it gives you better, more reasonable intuition into the results. And when the value is small, there's hardly any difference between the two. And then we talked about the fact that how do we actually compute this, the e-value? Well, so it's the product of the number of alignments, which is essentially just the product of the length of the input sequences times the probability that a single random alignment will score above S. And that probability is given by this summing up over all values greater than the one you observe of the probability mass function of the density of this score, and that's given by the convolution of W copies of the probability mass function of the score of one column, because the columns are independent of one another, and I'm adding W of them. So the distribution of a sum of W independent identically distributed random variable is given by the W fold convolution. That's this formula written right here, and that's what I need to compute. Let's skip that, and I said, well, if we want to compute it exactly, well, the first thing we need to do is to bin the possible score. So everything is discrete here. So this is what the probability mass function of one column might look like. So it's discrete, and this is the minimum value is 0, and the maximum is some maximal value. So I bin the results into n bins, And when I put them on a bin, I can start doing reasonably efficient convolution, but it's still slow. It's because the probability I need to estimate is very small, n needs to be very large, and the complexity of doing naive convolution, it's easy to convince yourself it's w squared times m squared, and that's going to be too slow. And the question is, can you speed it up? So fast Fourier transform-based convolution allows you to speed up convolutions, but in this case, at a horrible cost, because what you get is complete garbage. These are the values I'm interested in. This is what I get. I don't get anything, basically using FFT. And we talked about the reason why that is so is this identity, and just so that you would believe me, this is R. I just written here 1 plus 1 e to the minus 16 minus 1, you get a 0, and we can do it again. So you'll see that I haven't graphically plotted this result. And the same thing comes up in MATLAB as well. If you try it in MATLAB, this is what you get, 0. So that's a fundamental problem with machine precision. Where did my slideshow go? Okay, so that's the problem with the FFT convolution, and how can we get around it, and can we get around it? And again, I stress that the problem is the Fourier transform itself. It's not the fast Fourier transform implementation of it. Okay, so what can work is this. If we suppose for a moment that the probability mass function of one column, the thing that I need to involve W times, suppose for 1 second that it behaves like a decaying exponential. Well, in this case, what I can do is, prior to applying the FFT, I'll apply what's called an exponential shift. So I'll just take this probability mass function and multiply it by e to the theta x. And if I'm fortunate enough to choose theta exactly as alpha, then p theta is now flat. And when it's flat, and Fourier transform will have no problem with it. Because what the problem is, if you go back to looking at what's happening here, the problem is that you're trying to recover a huge dynamic range. This is log 10. So you're trying to basically recover a dynamic range of about 180 digits. You cannot possibly do that in Fourier transform, because working with double precision in any modern computer gives you about 16 digits of precision. And so the most you can hope for is an interval here of 16 digits. So as long as what you're dealing with is flat, you will be able to recover it. But when it has a high dynamic range, you won't be able to. At least the smaller part, you will be completely washed out by the numerical unknowns. So if you can flatten this thing, then it will work. And the thing is that first order, this probability mass function I'm interested in does look like an exponential. This is a result back from 65 by Hefting, which shows that this is the probability mass function of one column, and it behaves like e to the minus s essentially tied between two constants. So there is hope here. And I tried this idea. It's an algorithm that I call SFT, for shift of FFT. The idea is, so given S naught, you want to compute that shift theta so that if you look at the shifted distribution, it will be centered about S0. So this can be done using solving some numerically solving this large deviation equation. This m of theta here is the moment generating function of the probability mass function of one column. Everything here can be computed numerically. Let me show you the big picture with a graph. That's what is the algorithm doing. So this is what I'm interested in recovering, the blue curve. Okay? Now, if I just apply FFT, it doesn't work, because then I get all that noise that kills the value. Suppose for this particular example, let's suppose the value I'm interested in is right here. the p-value at 300, at s equals 350. This is the point I want to recover. And we saw from before that if I use FFT, I get noise at this end. Now, what happens if I apply this exponential shift, which I can compute, this thing I can compute numerically. And what this thing does, if I take that loop curve and multiply it by the function e to the theta naught times s, so this is just s. So it basically shifts this original distribution to the red curve. So the red curve is simply with the blue curve multiplied by e to the theta naught times s. Now, what you see right here is this thing is, the only thing I'm guaranteed by this shift is that the mean value of the red curve is exactly 350, which is the point I'm interested in computing. That's the only thing that I'm guaranteed. What, for these kind of distribution, what also fortuitously happens is that not only is it centered with the right mean, it also peaks at about that area. And that's critical, because the fact that it's peaking up here is what will allow me to apply FFT successfully. Because if I now apply FFT to this shifted distribution, right, what would happen is I will again encounter noise. I will again encounter numerical errors that will kill the smaller part. So, but the smaller part, notice, are now here. And the large parts are here, which is exactly what I want to recover. So this part I will be enabled now to recover. And that's basically the key of the algorithm. Okay? So I compute this theta naught by solving this equation. I apply this exponential shift. I do fast Fourier transform based convolution. Get the red curve. I don't really get the entire red curve. I just get this part of the red curve, but that's enough because that's the part I'm interested in. And then I just need to shift it back. And the reason all this thing works well is because this exponential shift and convolution commute with one another. The two operators can commute. So you can take one, then the other, or the other way around. So that's the reason all this thing works. Now, okay, so this works fine, but how do I know that 5 years from now somebody won't do an analysis of what I was just doing and show that, oh, he gets this awful numerical error? So how can I somehow guarantee that my approximation actually works well? Okay? So this theorem that I was able to show that you can actually control the error that's introduced by the FFT using this thing. Never mind exactly the exact shape of that. I don't expect you to follow what's going on just by looking at it for a second. What's important here is two things. A is that this object right here is exactly this thing I'm minimizing when I'm finding my exponential shift. So what happens is that the bound of the error is actually minimized for that my choice of theta that I chose anyhow to do my exponential shift. So that's one nice thing. The other thing is important is that this is actually something that I can compute. And because I can compute it, I can compare it to the number I got. If it's small relative to the computed probability, then I can trust my computed probability. If the error bound is large relative to the computed probability, I throw it out. I say, okay, do some other method to compute this. The error is probably too large. So that's basically the two things from here. Okay, I'm going to skip the rest. I mean, okay, so let me just say from the rest here. This is an extremely accurate algorithm. It recovers something like 13 digits of precision. So in other words, if you compute your number using naive convolution and you compare it to what you got, 13 digits are correct, which is incredibly accurate. But who the hell needs 13 digits of accuracy for an eval? An eval just needs to give you some idea. So, but that's not the interesting question. The interesting question is, the answer to this one is nobody. But can you trade some of this accuracy for speed? And yes, we were able to do that, but I won't bother you with these things. I'll just skip it. I'll say this, that this technique that I just showed you, we were able to apply to other problems in computing exact tests, where in an exact test you want to compute the significance of the statistical test directly from the underlying distribution rather than using some asymptotic theory, which is commonly done. And we did two such things together with my student Niranjan. We did it for the multinomial goodness of fit test and the Mann-Whitney test, which are classical statistical tests. Anyhow, let's go back to the eval. So remember what was the context, right? So I was looking for, well, what's the probability that I'll see an alignment with score greater or equal to S in the input set, assuming it's random. I said, oh, we don't know how to compute that, so let's compute the expected number of such alignments. And then there was this problem that people were not computing it correctly. Okay, so now I have a way to compute it correctly. So what did I learn from that? What I learned from that is that this is a bad idea to begin with. You shouldn't really use e-values in this context. And how do I know that? Well, there's the obvious criticism that e-values can only be computed assuming a null IID background model, and this can be a very cool match to genomic DNA, as many of you know if you worked in this area. But worse, much worse than that, even if you know that your background is IID, the e-values might not give you the right thing you're looking for. And how do I know that? It's because we did these simulations where we constructed 400 what we call twilight zone data sets, and I'll say in a second what that means. But basically, we guaranteed that the IID model is correct, because what we did is we drawn these sequences using an IID model, okay? Identically distributed, identically independent, distributed nucleotides. Then what we did is we implanted the motif in these input sets, and in these 400 input sets, we implanted the motif. But that motif was weak relative to the input size. So it was just barely visible relative to random motifs that are in this input set. Okay? So that's what is meant by twilight zone. So the motif is barely visible there. So we have a version of a Gibbs sampler. We ran it, and it successfully recovered the implanted motif in 288 of these 400 data sets. So because we know the implant, we know whether the program succeeds or not, and in 288 of these 400 times it succeeds. And now I have a way to compute the e-values of each one of those results.
Can I ask a question about that? It's given that these things are twilight. It is
what?
Given that these things are in the twilight zone,
yes.
The things that you embed, it's conceivable that there is a set of windows in your random data that actually together have a lower entropy, higher information score than the thing you implanted.
Sure.
If your motif finder now comes back with that alignment, would you consider that a mistake?
I do consider it a mistake for the purpose of this analysis, right? So yes, I agree with you that in principle the motif finder did its job, but what it gave me is basically random given the input sets, right? So given the, it was just, it basically should have, statistical analysis should tell me.
Question. How many could have theoretically have gotten right? Do you know that?
No, I didn't do that analysis, but part of the reason is because these motif finders have difficulties in finding the optimal thing, right? So that's part of it.
Is this your in-house program?
Pardon?
Is this a standard program or your in-house?
It's our program. It's a gig sampler basically, which has.
So I guess the point is your implanted motif. If you score, it's a 1 per sequence, and you score the correct alignment. It is in. Let's assume that your sampler finds the global minimum successfully. It's a very good sampler. But it could be that only in 288 or 400 data sets, the thing you planted is in fact the global minimum, because in the other case, like Eric says, there might be something else.
Yeah, that could very well be. Right.
Now, what you're saying is, it has found the global minimum. But
no, I'm not saying that.
I'm just saying it found
what I implanted.
Yes,
To
in
some
these cases.
Well, and of course there is some definition here, right? Because it won't find exactly, because it's sort of moves some of the sites it found, but it's sufficiently similar in some criteria that I declared, yes, it's successful.
I guess what I mean to say is that I find it very hard to interpret what 288 out of 400 means.
But I
don't
didn't
know
give
if
the
it was
but,
because it didn't find the optimum.
but that's not the point yet.
Okay.
That's
Sorry.
yeah, that's not the point. The point is now coming.
Okay.
Okay?
Sorry.
So in 288 of these 400, the motif finder found the implanted motif. So in my mind, this should be a success. Okay? But now I go and ask, what is the e-value calculated for each one of those 288 successes? The e-value should be rather small to indicate that there was a success here. But what I found was the e-value was huge. It was 10 to the 12. Meaning, the motif finder tells you that, or the statistical analysis tells you, that the motif finder found a motif.
I don't understand this p-value, because p-value should depend on the size of your sequence. It's certainly not 10 to the 12. You cannot have 10 to the 12.
No, it's the number. Remember what the definition of the e-value is. It's the expected number of alignments in your input set, right? Assuming the input set was randomly generated.
But of the same
score,
size. Of the
yes,
same size.
same size input set, same size alignment. What's the expected number of alignments that you would find in a random input set that score at least as high as what you found?
So what was the size of your input set?
It was substantial. It was, I think it was like 30 or 40 sequences, and each one of them was 1,500 or 2,000 nucleotides long. It was substantial.
So how can it be?
How can it be? Okay, just one second. So what's right? So this is exactly the same definition of eval as BLAST uses. What's the expected number of alignments that score above? But we'll get to how can it be. But what is clear is that this is. Remember, now I know that I'm computing the e-value correctly. I know my model. I generated it. Everything. I controlled everything. The numbers are correct. What the first message from this is, e-values are not the right thing to look at in this context, because if the motif finder gives you the right answer and your e-value is 10 to the 12, nobody in their right mind will believe that this is you found the right thing. Now, so let's talk a little bit of why is the e-value failing in our context, right? Because it works so well with BLAST. Why is it failing in this context? So recall this fundamental thing that Archul wrote. When the e-value is small, the p-value and the e-value are nearly identical. Now this holds for pairwise alignment problem, which is the BLAST problem, since the number of high-scoring maximal local alignments is well approximated by a Poisson distribution. So if you just ask, well, how many alignments will score above a certain threshold? Well, that's distributed, if that threshold is high enough, that's distributed according to a Poisson distribution. And for a Poisson random variable, you have this identity, but the probability that the Poisson is greater, or random variable is greater than 0, that's given by 1 minus e to the minus lambda. And for smallish lambda, that's the same as lambda, which of course is the expected value of the Poisson. So for Poisson random variable, the e-value and the p-value are roughly the same when lambda is small. That's why the e-value works so well for the BLAST case. Now, the reason it fails here is for the motif finding problem, the number of high-scoring alignments does not seem to follow the Poisson distribution. It's much clumpier, and by that I mean that consider that you have, if you have say 30, the alignment is made of 30 sites, right? And now you have a really good high-scoring alignment. Now if you change just one of those sites with some other site chosen from the same sequence, and if that sequence is long enough, you probably might still have something which scores very high. So what happens here is that once you get a high scoring alignment, all the aunts and uncles of this alignment comes in and join together because they're also very high scoring. So that's what I mean by it's clumpier. It's not so discrete, right? So once you have one, there's a lot of other satellites or parasites, depending on your point of view, that come and also cross the threshold. So you can have an e-value of 10, but that might still mean a very small p-value because that e-value of 10 might be because of just one, essentially one cluster of alignments that scores high that brings in a lot of other satellites.
You had 10 to the 12.
Pardon?
You had 10 to the 12.
Yeah. I mean, it's a big number, but I mean,
But you think
but that's part of the story. That's part of the explanation. Another part of the explanation is yet to arrive. So, okay. So whatever the reason is, it's clear that that the e-values are not a good thing to begin with. So that's. So it was very frustrating for me because I spent so much time on computing it accurately, and when I finally computed it accurately, I realized it's not the thing to look at. Anyhow, there were other things that I got out of that one. So anyhow, so let's go back to the p-value. So the p-value, remember, for a motif with score S is the probability that a now drawn input set contains a motif with entropy score greater or equal to S. So ignoring the fact, I told you I don't know how to compute it efficiently, but ignoring that fact.
Sorry, I'm just curious about this. You must have done this, the motif that you planted, the information score, for random data sets, did you calculate the motif with the best information score and its mean and variance and see where your implant motif fell there? Is it, so if you, did you generate your motif to begin with to be significantly different from what you'd expect for random?
No, it was on the contrary. It was constructed so that it is
borderline.
It's twilight zone, right?
So I can believe 10 to the 12 simply because there is such a huge number of alignments possible.
Right. Right. Okay. So back to this issue. So ignoring the fact that I don't know how to compute it, is it useful had I knew how to compute it? So again, going back to the same experiment, remember I had 288 successful runs. I asked how many of these will have a significant p-value computed this way. So we saw the e-value was conservative, how many will have a significant p-value? And the answer was at most 10% will be declared significant at the canonical 0.05 significance threshold. So in other words, had I known how to compute this p-value accurately, at most 10% of those would have been, 10% of those would have been called significant, even though they are successful runs. So that means it is way too conservative.
How did you calculate it?
Okay, yeah, so that's my next thing. How did I compute it, right? I told you I don't know how to compute it. Yeah, so what I can do, I can lower bound it, right? So I don't know how to find, the problem is I don't know how to find the best alignment, right? But I can run a plethora of motif finders on the data set and take the maximum of those. So that's still not going to be the best motif finder, but that's going to be a lower bound of that. So I can use that. So this is basically a lower bound. You're right. So, so why is the p-value failing? Okay, so I understood why the e-value is failing, but the p-value is, that's...
So you ran a plethora of motif finders on the same data set?
On the...
on real random stuff.
That's what
real random stuff and see what kind of things.
Right, so I was able to construct an empirical distribution.
Exactly, yeah. The same motif finder on...
No, I ran zillion of motif finders. Because now, remember, I'm interested in not... Ideally, if I could have a motif finder that would say, okay, this alignment is the best thing there is in this input set.
To calculate the p-value for this motif finder that found 288 out of 400, I should be running the same motif finder on synthetic data that does not
No,
contain
but
a
he
motif.
wants a p-value
No.
that says how often in such a data set is there a motif spuriously with at least this score.
I mean, there is, you're getting at something that if I have time I'll talk about, but this is not how the p-value was defined. How am I doing with the time, aside from the fact that the...
No, I mean, we are 15 minutes into lunch already, officially. So we have a late lunch. Some people are starting.
Do you want, so what do you want to do? I mean,
How much do you have?
What we could do, if you can break at this point,
Uh-huh.
there are only 3 posters there. We could do something after the poster session.
Yeah, that's fine. Yeah, I don't want to stand between the stomachs and the lunch, so yeah, that's fine. I can break this.
But I mean, if there's 1 or 2 more slides until you have a more natural point, then of course.
Okay, let me just finish here then. Let me just get to the point why the p-value is not working, then we'll stop. Just one more slide. So why is the p-value also failing in our context? Okay. So the problem is something that Rahul was actually getting at. So recall our coin example, right? So we had 100. We were tossing the coin 100 times, and we observed 75 heads, and we wanted to compute the p-value, which is what's the probability to observe 75 heads or more. But now imagine that we can't observe the coin directly. Rather, we rely on some absent-minded reporter who actually counts the number of successes. And that reporter is absent-minded, so he missed about 20% of the count. So instead of 75, it gives us back the number 60. Now, if we compute the p-value relative to 60 rather than 75, the significance is significantly altered. This is the original p-value. This is relative to 75. This is the p-value relative to 60. Huge difference, of course. Right? It gave us the wrong answer. But that's what happens with our motif finders. There are these absent finder reporters, because what happens is the difference from the blast problem, the blast is nearly optimal. You'd be hard-pressed to find a case where blast is not finding you the optimal alignment. Right? But the motif finders are very far from it. Motif finder is, Eric somewhat alluded to it. He said about the multiple alignment problem. He said pairwise alignment problem is easy. That's the blast problem. Multiple alignment problem, we don't really know how to solve it. And the motif finding in some sense is some manifestation of the multiple alignment problem, local multiple alignment, and we really don't have anything near an optimal solution here. Right? So there are these absent-minded reporters who gives you back something, but it's suboptimal. They don't really give you the best motif in there. They give you the best that they could have found. And that's the reason why the p-value, which is defined as what's the probability that the best alignment in your input set scores above S, is the wrong question to ask, because your finder cannot find those best alignments. Rather, you should really ask questions like what Rahul was saying, relative to the performance of the finder. And
It's going the wrong way, this argument, because that makes it even more ununderstandable why your motif founder found the motif you planted 288 out of 4.
Okay, but what you said was, when you said that, I understood you to say that they found all the sites, but in fact you're saying they
No,
found
I said,
pattern.
I particularly said that for some definition of found, there need to be some threshold. The thing is, in those experiments, if I look at what I implanted, that's actually a lot weaker than what it found. It was able to still come up with something that looked like the original motif, but actually improved upon it, borrowing random sites from the input sequences. Because the input sequences were long enough, it was able to improve.
But let's say there were 30 input sequences, it found your planted site in 20 of them, typically.
Something like that, or maybe a smaller number, but yeah.
So that again is really bad.
And the reason why the motif finder was actually able to succeed is because a successful, remember this is a good example, so because a successful, you see, a good alignment, as I said, it's this clumpy thing. A good alignment has really a cloud around it of a lot of motifs that are very similar to it that are all high scoring. Now, it's fairly easy for the finder to get into the cloud, but once inside the cloud, it cannot possibly, in a reasonable amount of time, get to the top of the cloud.
Most of the
That's-
opposite, actually.
pardon?
Once
I
you're
see
there.
a Bayesian struggling to get out.
I mean, if you put a prior on the number of expected sites in that sequence, then you'll probably.
No, but this is a simpler problem. This is the problem here is, the problem here is that each sequence has exactly one site. So this is an even simpler problem.
Also, the sampler actually only looks for one site.
One site in each sequence. This is an easier problem.
I'm a bit confused also, but I think we should go to one.
Yeah.
So we'll meet at 2:10. Will that work?
Yeah.
Quick lunch 2:10, and like yesterday, we'll fit in time for